ME347, Example 22. For this problem, use the same system described in Example 19 and the same pump family, which is the Peerless 4AE12 pump family operating at 1750 revolutions per minute. For Part A, estimate the pump curve for the 11-inch diameter pump from the operating point for one pump and shutoff head at zero flow rate. For Part B, calculate the new operating flow rate and head for two of these pumps in series. For Part C, calculate the new operating flow rate and head for two of these pumps in parallel. For this problem, we will need to make the same assumptions made to calculate the system curve in Example 19. These include the following. First, we assume steady, constant property flow of Antonian fluid, which is water at 60 degrees Fahrenheit. Second, we assume that the water in the large tank has a constant height, that is, open to the atmosphere, and that the velocity at the top is approximately zero. Third, we assume fully rough turbulent pipe flow near the operating conditions for the pump. An additional assumption we need to make for this problem is that the piping needed to add a pump in series for Part B and to add a pump in parallel for Part C adds negligible major and minor losses. Let's begin by looking again at the schematic diagram from Example 19, which shows water being pumped upwards from a lower tank to an upper tank. The water in the lower tank first enters the piping through a re-entrant entrance with a loss coefficient of 0.78. Then it goes through 10 feet of piping and one elbow before the pump suction inlet. After the pump discharge, it goes through 40 more feet of piping and one additional elbow before flowing into the upper tank through an abrupt exit with a loss coefficient of 1.0. For both of the elbows, the minor loss is given in terms of an equivalent length of straight piping. Note that the pipe has a diameter of 3 inches, a roughness of 0.0050 feet, and a total length of 50 feet. Also, the change in the elevation of the water before the pump is 5 feet, and the change in elevation after the pump is 20 feet. So the total elevation change is 25 feet. Note that this data was used in Example 19 for Part A to find the system curve, and for Part B to find the operating conditions for the 11-inch diameter pump, as shown. For Part A, estimate the pump curve for the 11-inch diameter pump from the operating point for one pump and shutoff head at zero flow rate. To begin, we will use a second-order polynomial or quadratic function for the curve fit defined as shown. Note that experimental tests have been used to demonstrate that this function provides a reasonably good curve fit for pump head versus flow rate data. Since we have just 2 points for our curve fit, we can solve directly for our two curve fit parameters, which are h sub naught and c sub p. Typically, we would have more data and then use least squares minimization to solve for h sub naught and c sub p in order to get the best curve fit to all of our data. First, to begin our calculations, we note that h sub naught is just our specified shutoff head of 125 feet. Second, we solve for c sub p in terms of the pump head and flow rate, then input our operating data point values, and finally get a value of 790,000 feet per gallons per minute squared. Third, we substitute these values into our function to get our pump curve for a single 11-inch diameter pump. For Part B, we calculate the new operating flow rate and head for two of these pumps operating in series. This means that the discharge side of the first pump is directly connected to the suction side of the next pump in series. Thus, the volumetric flow rate will be the same through both pumps by conservation of mass for an incompressible fluid. In addition, the pressure rise or pump head rise across each individual pump will be approximately the same for the same pump design. Thus, to get the pump head curve for the two pumps in series, indicated by the subscript 2, we multiply by 2 the pump head curve for our single pump, indicated by the subscript 1. This results in double the pump head at each flow rate. Then, to get our new operating point for the two pumps in series, we solve for the intersection of the pump and the system curves by setting these two functions equal to each other. We then solve for an equation to solve for the new operating flow rate. Next, we substitute in values from our single pump curve and from our system curve from example 19. For the operating flow rate, we get 603 gallons per minute. For the operating head, we can use either our pump curve or our system curve to get the same result. Here, we have used the system curve to get an operating head of 193 feet. For Part C, we calculate the new operating flow rate and head for two of these pumps in parallel. This means that the flow goes through a T-fitting, so it can enter the suction sides of both pumps at approximately the same flow conditions. Then, a second T-fitting is used to bring the flows back together on the discharge side, once again at approximately the same flow conditions. Thus, the pressure rise across each pump will be approximately the same. Furthermore, for the same pump head, the flow rate with two pumps in parallel will be about double the flow rate for a single pump. Note that this is based on our earlier assumption that the minor losses for the added T-fittings and piping are negligible for this system. Depending on the relative magnitude of the T-fittings to the other losses in a given system, this may not be an acceptable assumption. Thus, to get the pump head curve for two pumps in parallel, indicated by the subscript 2, we set it equal to the pump head curve for a single pump operating at half the flow rate, indicated by the subscript 1. This results in double the flow rate at each pump head. Then, to get our new operating point for two pumps in parallel, we solve for the intersection of the pump and the system curves by setting these two functions equal to each other. We then solve for an equation to solve for the new operating flow rate. Next, we substitute in values from our single pump curve and from our system curve from example 19. For the operating flow rate, we get 456 gallons per minute. For the operating head, we can use either our pump curve or our system curve to get the same result. Here we have used the system curve to get an operating head of 121 feet. Finally, let's compare how the operating points shift for the case of two pumps in series and the case of two pumps in parallel. For both figures, the system curve and the pump curve for a single pump are shown. For the figure on the left, the pump curve for two pumps in series has been added. Note that the pump head at each flow rate is double for the two pumps in series as expected. For the figure on the right, the pump curve for two pumps in parallel has been added. Note that the flow rate at each pump head is double for the two pumps in parallel as expected, but it is harder to see this on the scale shown. For our system curve, which is fairly steep, the operating points shift to a much higher flow rate and pump head for the pumps in series than for the pumps in parallel. Thus, using pumps in series would be a much better choice for this system. However, if we had a much flatter system curve corresponding to significant elevation change with negligible major and minor losses, pumps in parallel might be a better option.